Good afternoon, everyone. My name is Matti Palomäki. I work for VTT, responsible for quantum computing applications and also the service platforms.
You say click.
Click. Just starting with, you may wonder actually that the research center is running service platforms that in Finland, that's how we have decided, just to lower the barrier to everyone. And this is the latest computer we have. We have already introduced actually 3 computers. This is the IQM 50-qubit computer that we have currently in use, and it's also connected to the Lumi supercomputer, and you can have also pulse level access from there. Click. And very advanced also QX interface we have evolved, so it's quite nice to do jobs with the quantum computer. Click. We have also already multiple companies using the system, and some have also completed the projects. Here are a couple of them. We have done also ourselves multiple projects already, and a few companies mentioned here who have also used the already computer and completed the project using that. Click. And there is also a roadmap in the future. We are also introducing a 150-qubit computer next year and 300-qubit year 2027. Click. And this is kind of an announcement now that we have kind of an opened application period today. Actually, you can apply free of charge quantum computing time using our service. There is kind of a maximum of 20 hours you can apply, but you need to justify the time. And of course, for the project, there is some kind of criteria. We are looking that one. And this is applying this European Union area and also broader than that. So you can contact me directly or using the website address here. Thank you.
Perfect. And hand it over. Thanks a lot. And hand it over there. And all the pictures are going to be also presented here at the posters. So we go to number 2. And
okay.
You take it away.
Okay, so the software I present is Dynamiqs. So it's a library for simulating open quantum system on GPU, and that is differentiable. Click. So when you want to simulate a Lindblad master equation, for instance, with an Euler method, you have to compute commutators and action of the jump operators. Those are just matrix products. So good idea to just use GPUs that are designed for that. Click. Yeah. And another very important part is that usually, so you have parameters, you have your system that depends on those parameters, then your solver can evolve the state to have the end state after evolution taking into account those parameters, and you evaluate some real functions, for instance, average value of an observable. With Dynamiqs, a very nice thing is that everything is differentiable. Click and okay. And so you can compute the gradient of that function as depending on those parameters, and that allows to use a gradient descent algorithm. So this is very convenient if you want to do parameter estimation, for instance, to compare with experiment results or to do optimal control or other stuff. And to compute the gradient, there are actually tricks, I won't dive into them, to avoid blowing up the memory. So under the hood, Dynamiqs is based on JAX and diffrags for the ODE part. So if you take normal Python, it executes the code line by line. With JAX, the program is traced and a graph of operation is built. There can be optimization on it to optimize it for hardware, and also it allows the differentiability. And so, as I said, ordinary differential equation solving is all handled by diffrags, which is a specialized library. One thing to know about Dynamiqs is that the API is very similar to the one from Qtip. And we can switch to the last slide. So Dynamiqs is an open source project. We are also welcome any contributions, so don't hesitate to use it and to contribute.
Thank you. Number 3 by Quinn.
All right. Hello, everyone. My name is Quinn, and today I'll be pitching a new quantum error management compiler called QuantEM. Click. So right now we're in this transitional stage. It's going from NISQ to full error correction, and as a consequence, quantum error detection has emerged as an intermediate strategy that sits in between error mitigation and full error correction. However, without any proper tooling, the burden is on the developer to manually insert these QED codes. And of course, this is time-consuming, error-prone, and just not scalable. So as a solution, we present a compiler that automatically integrates the QED codes into any arbitrary quantum program, and thus removes that burden from the developer. So as you can see here, this is the workflow for Quantum. First, we take it as input the quantum program and the hardware layout. Also, the user can specify the QED code. Then we go through the program analysis and transformation module. This module is responsible for analyzing logical circuits and determining the best subregions to incorporate the QED code. Also, if the QED code was not specified by the user, we can decide the appropriate QED code based on the circuit structure and the underlying hardware layout. Then we pass through the error detection code integration module. This module is responsible for the mapping of the logical to the physical qubits. And this is the key module that really differentiates QuantEM from the standard compiler, and that is that QuantEM actually tracks which gates belong to the QED code versus the original program input. So as a consequence, QuantEM can optimize and prioritize the mapping of the QED code itself so that we mitigate the number of swap gates that occur on that QED code. Finally, before hardware execution, we go through the post-processing and resource management module. This module estimates the overheads associated with the hardware execution. Then it takes the counts, post-processes those counts, filters them based on syndrome measurements, and from the syndrome data, we can optionally update the noise estimates based on the syndrome data, or we can incorporate resource-efficient extrapolation techniques based on the number of SILAs that have been allocated, and improve program outcomes. So if you're interested in learning more, you can check out the poster in the back corner. I'm also open for discussion anytime, and this is available on GitHub under the name QuantEM. Thank you for listening.
Thank you much. Next, we have Giuseppe.
Hello, everybody. Today I want to talk about our newest tool, that is QSimBench. Yes, it's another quantum benchmark tool, but we called it an execution level benchmark. Click. Why we define execution level? Because we want to focus on another aspect of the quantum workflow. So as Lucas said, we want to test tools. In our case, we want to test tools that work with the result of an execution. So the idea is that you want to test a tool that when you execute a particular circuit on a particular quantum computer, and want to work with their distribution and do some analysis, like post-processing, for example. The idea is that you can use QSimBench, and you already have different quantum algorithms for different sites, for different quantum computers, and we already pre-computed, stored, and organized all their shots, all their distribution output, up to 20,000 shots. And you can use it, you can use for inference, you can use it in a randomized or sequential way. So the idea is that with QSimBench, in milliseconds, you can do what even with the quantum simulators, you need, for example, hours, if not days, because you already have all of them, and it's also memory efficient and storage efficient. So you download only the data you actually need for your computation. We are now extending it with a real quantum computer with more algorithms and also more bigger circuits. So, and another nice thing is that in this case, the size doesn't matter. If the circuit is 4 qubits, 15 qubits, 30 qubits, You have to pay more memory, but the time you need is always the same. So let us know if you want to use it, some extension, and thank you for your attention.
Thank you very much. Niklas is next.
Hi, I'm Niklas. I work at Fraunhofer Focus, where we develop Qrisp. And Qrisp is a high-level abstract quantum programming language developed in Python, and it's fully open source. We have a couple of tools that enable you to easily write algorithms. One of our main concepts is, as you can see in the upper left, quantum variables, which abstract away qubit management from the user. Oh, no click. I just had this one slide. Can you go back? Okay, well, anyways, so we have quantum variables, which abstract away qubit management from the user. Then we have also arithmetic tools, which are meant to be used on quantum variables, such as quantum floats, to perform additions, etc. We have an extensive algorithm tool bench that is already pre-existing, which you can see here: quantum backtracking, Hamiltonian simulation, Shor's algorithm. Quantum backtracking you will not find in any other toolbox. But what I'm mainly here to talk about today is our newest feature, which is called JASP, which JASP stands for JAX in Qrisp. So Qrisp uses Python, is written in Python, and Python has the main problem of compilation speed. So as a solution, we implemented an alternative compilation pipeline, which leverages Google's JAX. So the full pipeline, you can see here on the right side, which JAX is embedded in. We're able to compile down to QIR, so we can pretty much run it on any hybrid backend. All of this enables us to perform retile computations with repeat until success procedures, and enables algorithms such as LCU, HHL. Especially LCU is something that I also have on my poster, and I will be very happy to go into the implementation with you if you want to check that out. Well, that's it from my side.
Perfect, thanks a lot. Ralf is next. And Ralf?
On my own.
Sure. This is...
Thank you. My name is Ralf Ramsauer. I'm from the Technical University of Applied Sciences in Regensburg, and I'm going to present our ongoing work on system-level Quantum-Accelerator integration with QAL. You all know quantum computing platforms advance rapidly. They exist of many more or less loosely coupled components, such as hardware and software for control electronics, infrastructure for compilers, or orchestration software. These components have grown organically around experimental needs. And this structure has enabled great scientific progress, but as we look towards broader industrial applicability and industrial integration, the challenges shift slightly. Future quantum workloads rely on tight, low-latency coordination between quantum and classical resources. Achieving this determinism across heterogeneous systems is increasingly important if we want to realize practical quantum advantage. So our motivation is therefore to explore how tighter coupling between quantum and classical components can be achieved. Not by replacing existing approaches, but by defining a coherent architectural perspective that supports both flexibility and real-time performance. So our architectural approach addresses this challenge from user space down to the hardware. At the top, user space applications and established SDKs, Qiskit, MQT, and so on, interact through a unified system interface that abstracts away hardware specifics. Inside the operating system, a quantum abstraction layer that we call QAL manages scheduling, communication, and resource allocation, providing an abstract but consistent interface between classical hosts and quantum devices. To evaluate the OS layer against actual hardware, we develop, in addition, virtual hardware models that capture the expected behavior of future devices. These models are tested within emulated environments, allowing iterative refinement and fast architectural changes. Once these interfaces mature, we deploy the same models on FPGA-based prototypes to analyze real-time characteristics and latency effects under near-realistic conditions. So how does it look like in reality? On the left side, you can see a Linux system running our integrated stack, and on the right side, you can see an FPGA-based prototype to analyze real-time characteristics under real conditions. So this stepwise approach lets us fully study the full stack integration and predict realistic performance behavior at scale, well before physical quantum processors become available at scale. So if you would like to see this in action or discuss how such an architecture might connect with your work, I am happy to talk to you right there at our poster booth. Thank you.
Thank you. And Matteo is next. Here we go. Graphics.
Yeah, all good. Okay, hi everyone. So I'm Matteo. I work at the INRIA Institute in Paris, and I'd like to introduce you Graphics, which is our open source Python library for measurement-based quantum computation. So measurement-based quantum computation, or MQC for short, is an alternative to the circuit model. Here, computation happens through applying adaptive single-qubit measurements on an initially prepared entangled resource state. And MQC shares primitives with error correction code, such as this feed-forward, and it can also be useful for optimizing circuits and, okay, next one. Yes, so in MQC, instead of circuit size set, we have patterns, which are a sequence of commands. So for instance, creating and entangling qubits, or doing a measurement. Now, in graphics, these patterns are the central object. We can directly initialize them as a Python list of commands, or we can transpile them from a circuit or CX diagram. Now, once we have this pattern, what we can do is to standardize it and compose two patterns together, following the rules of measurement calculus, but we can also exploit this pattern representation to optimize the original circuit. For instance, by doing an efficient simulation of the poly measurements, minimizing the ancilla qubits in the pattern. It's fine. Yeah. Graphics also offers tools to understand the structure of the computation. We can, for instance, visualize the underlying graph of the pattern and the correction sets, and we can compute the flow of the open graph resource state. We can also simulate these patterns with various built-in backends, so state vector, density matrix, which supports noise, and tensor networks. And very recently, we also added a symbolic backend, which allows us to work and simulate parametric patterns. And finally, I'll just mention that we have developed and continue developing plugins to run these patterns in actual hardware machines. In particular, there's an interface with Qiskit and with Perceval for photonic QPUs. And we can also export these patterns in the form of an OpenKSM file. That's it. We have a poster list. If you want to know more about it, please come by. And in any case, thank you.
Thank you. Next is Barak. From Classic, yeah. But, yeah,
it's Dror finally.
Oh, okay, yeah, you changed the speaker. Sorry for that. Yeah.
No problem.
Here we go, and you take it away.
So, hello everybody. My name is Dror Segman, and I'm a product manager at Classic. Phase oracle is a really widely used building block in many algorithms, including rovers. In this short pitch, I'd like to show you how you can use our quantum modeling language QMod to define a phase oracle in just a single line of code. So let's start. Click. We define a quantum function named phase oracle, which gets a single input variable v, which, as you will see in a moment, holds all the quantum numbers required for our model. Click. The function uses a control statement, which has two parts. The first on the left is the condition. In this case, an arithmetic expression. And for any classical state that satisfies the condition on A, B, and C, our quantum numbers, the operation is applied. In this case, a phase flip. So we use quantum numbers, arithmetic expressions, a control statement, and a phase operation to achieve our goal. Now, this is not just a mere description, because click, our synthesis engine takes this nice and precise description and creates an optimized implementation, gate-level implementation, out of it. And you can choose on which quantum resources to optimize it, as well as under which constraints. for example, in order to meet the specs of your favorite QPU. So now we have at hand a precise description and an optimized implementation. But as we all know, nobody really likes black boxes. And that's why we have our visualization tool that lets you go from the high-level description and expand it, click, as much as you like, till you reach the low-level implementation. This was the high-level version of my pitch. If you'd like to expand it further, please feel free to reach out. Thank you very much.
Terrific, thank you. Really good. Next we have Stephen.
All right, thank you. I'm Stephen from Coro, and I'll be presenting our company and our latest software called Divi. So the problem we tried to solve is that monolithic quantum computers don't scale. We know that they're going to require many qubits. We know that many qubits in the millions don't fit on a single quantum computer. And so in order to move from monolithic quantum computing to distributed quantum computing, we need to build a network stack. So Coro builds this for today and tomorrow. In our current implementations, we're looking at integrating quantum computers with high-performance computing. So we don't use quantum networks the way that you see in literature, but we use them classical networks to do distributed computing. And in the future, we're looking at building a network operating system that allows quantum computers to share quantum information between each other. Next, yep. So we're building a software called Divi, and Divi is different than other software in that it builds large workloads in one go. It's not an iterative approach that some other tools would provide, but we try to build big workloads, so that is the orchestration aspect that takes care of the optimization. In this example, we've implemented protein folding from an IBM paper in 2021. With 20 lines of code, we can define the Hamiltonian, we define an optimizer, we connect to the service, and then we build out a VQE program with parameters only. There's no writing of quantum circuits explicitly. And Divi handles this big workload generation. We're using population-based optimizers, so that it's orchestration and not up to the user to write tons of code for this. What's actually happening under the hood is there's a various set of components that we build services. First is Divi, of course. It tries to minimize workload. Then we go to Composer, which does orchestration, which interacts with hardware and reads the hardware state so that we can build good schedules. And then Conductors interfacing with different backends simultaneously. So it can go to different vendors. It's vendor agnostic, and it's also simulation enabled. And in the end, to show what happens here is we have a Hamiltonian. It might have 335 terms in it. It means you have to run more than 300 circuits at least, but because we use population-based optimization, it's 100 terms. 100 circuits per term. And then when we build a naive implementation of VQE, we might have 30,000 or 30,000 circuits to run per iteration. And what happens is with our software, I will continue, we can think about, okay, a naive implementation of this means you have to implement VQE, you have to connect with all the interfaces to the hardware. There might be thousands of lines of code. If you use Divi, it goes down to 20 lines of code, and then if you want to do additional hardware parallelization, it's 0 lines of code in addition. So per iteration, if you run this, it might cost $100,000 per iteration. So if you want to run 100 iterations, you can imagine the costs. When you use Divi, we do automation to reduce the workload, goes down to hundreds of dollars. And again, with Composer at hardware level parallelization, $50 per iteration. It's a massive savings. And just to show this actually works, I mean, we're running on noisy hardware, of course. It's not going to be perfect. Blue is simulation, red is hardware. Optimization problem is coming down as expected. And it's, as one would usually see if you just ran it naively with IBM hardware. So our poster's in the back. If you want to see a live demo of this, if you have any more questions, feel free to contact us. Thanks.
Thank you. Next is Roshi. Sure.
Hi, I'm Hiro Nakata from the JIJ. We are providing the optimization-focused developer platform. So before going to that, let us introduce our company. So, okay. We already provide over 50 use cases in a variety of the industries. If you'd like to know more detail, please let me know. So the JAJ is the headquarters is located in Tokyo, but I live in the UK, and we plan to establish a branch in Hamburg in the next year. And so I'm the board member of the QStar, Japanese Industry Consortium. If you'd like to collaborate in the Japanese society, please let me know. And so we have the various of the integrated team, the quantum optimization, the ML, the sciences, computation, OS, and the commercial experts. And this is held in the last August IEEE. We got the Best Paper Award. Also, we contribute a finance service in the UK. And then, so this showed the optimization workflow. It doesn't matter the classical and the optimization. So the classical approach, this has a modeler and the solver. They are already the product. But the quantum software is currently in the right in the hand. So we cover the sort of the workflow from the modeling to the post the process. So we collaborate with Qiskit and QuickQ and Penny Lane. If you'd like to collaborate, please let us know. Thank you.
Thank you. Then we have Felix next.
Yes.
No?
Perfect. Hello, everybody. My name is Felix. I am a PhD student at Imperial College London, and I'm going to pitch to you a software package that I started making earlier this year called DISCO. So DISCO stands for Distributed Quantum Circuit Optimization. This is about optimizing circuits for distributed quantum computing. But unlike what Stephen said earlier in his pitch, we're considering quantum circuits which are actually executed over quantum networks. And so in this case, we need to execute our circuits using teleportation. So we need to distribute entanglement between QPUs. And we want to optimize the entanglement that we are using because we expect it to be much noisier than what we do locally. And so we use a graphical formulation of quantum circuits which has a temporal dimension in order to allow us to optimize over a very wide variety of teleportation primitives. And this allows us to quite greatly reduce the amount of entanglement we need between QPUs. And really what DISCO is designed to do, it's designed to take a circuit, transform it into a graph, take a network, and spit out a distributed quantum circuit, which is something you can pass into other compilers for further optimization. And under the hood, we make use extensively of techniques that have been very successful in large-scale graph partitioning, and we adapt them to the specific case of quantum circuits. So particularly, we use two different kinds of coarsening. We coarsen the graphs that we use, and we also coarsen the networks over which we partition them. And this allows us to do hierarchical or multi-level partitioning, which drastically reduces the amount of compute and also improves the amount of entanglement that we need. So in terms of flow, you put in a quantum circuit, you convert it into a graph, you define a quantum network, and then optionally you will pass in a graph coarsener or a network coarsener, and you will pass the result of that into a circuit extractor, which will define a circuit that has some immutable blocks that use entanglement, and you can pass the rest of it into your further compiler workflows. Thank you.
Thank you. So Stefano's next.
Yes. Perfect, thanks a lot. My name is Stefano Carrazza. I am from the University of Milan. I thank the organizers for the opportunity to be here and talk about Kibo. Please, next. So Kibo was born in 2020 and is a modular framework that tries to complete all the middleware features from models and applications, simulation tools, lab drivers for control electronics, calibration tools, and remote access. Every year, we try to release a new package and a companion paper with benchmarks and results comparing the performance. So, as I mentioned before, for quantum simulation, we are supporting state vector simulation and tensor network simulation approximations by using our own code, optimized with just-in-time algorithms, but also with the possibility to interface with NVIDIA and external providers. And for the lab users, we have the Kibo Lab driver, which implements all the Pulse to drive interfaces to commercial products, such as quantum machines, cuBlocks, Zurich instruments, and so on, but also to open hardware, like open firmware from Fermilab with the KIC project. And with this in mind, we can also go ahead and perform automatic calibrations of single qubits and multi-qubit setups, basically on superconducting systems. This year we have released a cloud system that is available that you can use for executing jobs on different providers from multiple institutions. And last week we have released a special module for machine learning, like QuantML.
Thank you.
Yes. Just a few words. People using the code is from Italy, from the National Institution, the Singapore National Computing Hub, and the Middle East. And we are also hiring, so if you are interested, please, we can have a chat on the poster on the left. Thank you.
Thank you. And since we don't have enough cues here, thanks, right? So it's new for me. And next one is Andre. Here you go.
Okay, hello everyone. My name is Ondřej, and I will talk about AutoQ. This is a joint work between Brno University of Technology, Czech Republic, Taipei in Taiwan, and Uppsala University in Sweden. Click. So your mother sent you a quantum circuit and claims that it will give you a cake if you run it on your fancy quantum computer. So do you trust her? Well, it's your mother, so you should, but she has never been very good in linear algebra, and also the delivery company might have flipped some gates for something else. So we want to help you. So in AutoQ, you can use some quite high-level specification of what the circuit should be doing, and we can verify that it is doing the right thing. Instead of talking about unitaries, we have some more high-level specifications. So there is examples for Bernstein-Vazirani. You can specify, I start with the O0 state, I run the Bernstein-Vazirani with some secret oracle, and I get the correct output. For Grover, you can also say something like that. You start with O0s, you run Grover, and then because you don't really want to count the amplitudes for Grover, you can just have some high-level specification saying, like measuring the probability of the correct solution is bigger than 7/8 or something like that. We also support some parameterized verification. So if you have, for example, a way how to obtain the GHZ state for any number of qubits, we can verify that your way is correct for any number of qubits. Everything is based on a tree automata and satisfiability model theories from theoretical computer science, but don't be scared. You can use high-level specification without knowing the details. It is quite scalable. Scalable is like the runtimes are similar to the runtimes of quantum state vector simulators. As I said, it supports parameterized verification like Bernstein-Vazirani, GHZ, adder, quantum error correction, syndrome extraction. We managed to find some bugs in QCEC in some repeat until success circuits. We're also looking for partners for a quant era project, so if you're interested, let me know. And also talk to me if you're interested in participating in some competition about quantum software, like simulation, verification, synthesis, and so on. Thank you very much.
Thank you very much. Our mothers will be very glad to hear that. Santana and Stefan is next. Sorry.
No voice.
Go.
Okay, there we go. So my name is Stefan. I'm from the Software Competence Center Hagenberg. We are RTO located somewhere near Linz in Austria, and we're doing a whole lot more than quantum computing, but obviously, given the event, I want to focus on quantum computing today. Click, thank you very much. So yeah, the images that you see behind me should look familiar to you if you've ever heard about hybrid quantum computing, if you've thought about the software stack. So what are we doing differently? Our mission is to go a little bit from the other side, to not go from the bottom of the stack upwards, but go from the use case downwards to the stack towards the quantum hardware, towards possible simulation if you're doing something in the meantime where quantum computers are not available. And of course, what we're doing then is we're always on the lookout for use cases, for applications that we can run our experiments on, and where we can move through the stacks that are existing towards the quantum hardware to see for small-scale examples if certain problems from industry lend themselves to be solved on quantum computers. And this also goes above what the standard problems like MaxCat and the such that you usually solve on the quantum computer. So my shout out to you would be if you have any ideas, if you have any comments on hybrid quantum computing, either from the compiler side, from the hardware side, and of course from the application side, meet me over there at the poster and let's have a talk during lunch. I'm also here for the whole day today and the whole day tomorrow, and I would really love to get talking about this topic. Thank you very much.
Thank you. And now we're going to have Santana. Wait. No, we're going to have Jorge. Also fine. Also fine. Sorry, go ahead.
Thanks for that. Hi, everyone. So given that we are in the Munich Quantum Software Forum, I will just assume that you have at least heard of the Munich Quantum Software Stack. and the rest of the whole deal. So back in the day, the Leibniz Supercomputing Center, those crazy folks implemented and deployed the MQSS, the earliest version of it. And to the best of my knowledge, I believe we were the very first ones in Germany demonstrating HPC-QC integration. And so we have that working on. It's fine, it's there. Along with IQM, we achieved that milestone. But now we need to think about the future, what is coming next. And one of the things that are coming next is error correction, right? And you know better than me the constraints, but one of those is obviously shorter latency. And so what we're thinking is, or at least this is what I'm trying to, this scenario put it in my head. Maybe at some point the hardware providers will provide hardware, and the software providers will provide software. And it is the software the one that will have to talk to the chips at some point, potentially. So we have to be ready for that case. And for that, you need a stack that understands pulses. So in short, what we did is to identify the challenges in the stack, basically what has to need to be modified for the thing to understand those abstractions. And then we just propose a bunch of solutions. There should be, yes, at the very bottom, that one QR code brings you to a paper that we published along with all of those folks, because this is obviously not, only a couple of guys working on it. We are collaborating with IQM, with the German Aerospace Center, with AQT, like all the providers at LRZ are helping us to make sure this is compatible with those technologies. So in that one paper, you can find the details, what we are proposing. We are proposing, for example, to extend the QIR specification to support pulses. You can already find that work stream. We are also working on bringing support to the QDMI specification, which I believe you already know. That one is already public. You can find it there. And I think this is the exact moment when you guys should, join the conversation, join the discussion. Let us know what we are doing wrong, and just help us out. The poster is over there. Please do join the conversation. Otherwise, if we do it by ourselves, maybe we do it wrong. So we really need you guys. Thank you very much.
Thank you. And then Jabox, I hope I pronounced it correctly, is next.
Closer.
Close enough, okay. No, here you go.
Hi everyone, my name is Szabolcs. I'm very glad to be here, and I'm excited to showcase the QCR toolkit that we've been working on for the past year. We have heard about quantum circuits today, and I'm sure we will hear a lot more in the upcoming sessions, but one thing remains challenging, and that's reproducing quantum circuits from literature and papers. And it's challenging due to one fact. Implementation details are often omitted or partially documented. And this means that we have to manually put the pieces of information together from different sources, and that can take up to days or even weeks. We have talked with researchers globally and confirmed that this is a universal problem. And this is something that should be instantaneous, and this is where QCR comes into the picture. QCR is short for Quantum Circuit Repository. It's a dedicated place for quantum-specific algorithms and circuits. You can go to this website and explore and discover different circuit implementations. You can search using tags, use packages, quantum models, and so on. And for each circuit, you also find different representations that can include code, assembly languages, or circuit diagrams. You can also simulate the circuits directly in the browser and reproduce the results either as the uploader uploaded it or using different initial states. If you're a researcher working with quantum circuits and you upload a circuit to QCR, you also get the permanent ID, which you can use in your paper to cite this entry on QCR, so others can easily find all the necessary information. But what if you want to learn about quantum circuits or quantum computing in general? And this is why we started working and extending QCR with a secondary platform, QCanvas. QCanvas provides a two-dimensional interface very similar to Miro or Draw.io, but dedicated for quantum computing education. You can use built-in elements such as text, annotations, shapes that you can drag and drop onto the canvas, but also more advanced plugins. We actually developed a circuit designer plugin that works in a paradigm-agnostic way, which means you can simulate photonic or qubit-based circuits on the same canvas, and the simulation results, along with the visualizations, will appear directly onto the canvas, and everything is draggable, movable, and resizable. You can use QCanvas to create interactive documentations, lecture notes, or build a whole curriculums module in one platform. If you're an educator, student, or researcher working with quantum circuits, please feel free to reach out to us. We have a poster right there. we are here for the rest of the event and looking forward to talk with you. Thank you.
Thank you. And Eric is next.
Hi guys. I'm presenting our software package Topico, which is bridging the gap between material simulation and quantum computing. And so what we do is we use Quantum-Accelerator as a DFT software, which is basically like maybe you have heard of Hartree Fock. And if you do simulations of materials or crystal structures, DFT is mostly used. So we start out with a material, we define a crystal structure, then we do a DFT simulation. With Quantum-Accelerator, we read out all the output from Quantum-Accelerator, and from this we build a many-body Hamiltonian. And this many-body Hamiltonian can then be solved for, like with VQE or adapt VQE, quantum phase estimation, or any other algorithm to find the ground state, or maybe excited states. And from this, you can calculate then material properties. And we use this code as a whole pipeline, so we define the material and go all the way to the property. But you could also stop right at the many-body Hamiltonian. So, for example, if you don't want to use molecules anymore in a minimal basis set, you could just do a Quantum-Accelerator DFT simulation, use Topico to get a many-body Hamiltonian and test out your quantum algorithms you already have, because I mean the Hamiltonian is all you need to do simulations. And so we tested this out on some property, click, and which is the Bader charge. And this is basically where you can assign a charge to each atom in your crystal structure. And from this charge you can describe charge transfer in your material, or general charge distributions, or bonding scenarios. And so what we found is that we start out with the black data points, which is just a very simple DFT calculation. And our many-body Hamiltonian, after we solve it with Topico, is in red. And what we see here is that we compare it to sophisticated DFT plus U calculations, where people put really much time into that to get these results. And we see that by just running this simple DFT calculation and using our post-processing tool, we get data points that are much closer to the DFT plus U results than compared to just standard DFT. And this package is freely available on GitHub and web installable. So check it out. And my poster is in the back left. Come and see me.
Thank you. This brings us to Michael.
Hello, my name is Michael Bauer. I'm Senior IT Consultant for Quantum Computing at Evident here in Munich, and I'm going to present you Captiva HPC. So, you may already know the existing Evident Captiva platform, formerly also known as Atos Quantum Learning Machine. This is a full stack development environment where you can develop your quantum program. You can emulate them on classical hardware for all major paradigms like gate-based annealing and analog. It also has optimizers and compilers for your algorithms, and you can use it to integrate with real QPUs and integrate the real QPUs into an HPC system. Up to now, this was running on a dedicated classical appliance, so with a specific hardware with a large amount of RAM in order to be able to simulate up to 41 qubits. And now the new thing I'm presenting you now is that we are now also offering a software-only solution, which doesn't require specific hardware and runs on any HPC cluster with Linux and Slurm. And this, at the moment, contains these emulators. So you can run the emulators directly on the HPC cluster without need for special hardware, although it still plays very well together with the Captiva appliance if you happen to have one. So here on the right, you see an example of a hybrid quantum job, like Guava, for example. The user submits the job from the login node. Then on the main node, the job will be optimized for the execution on the cluster, and so the validation optimization steps are running on the main node, but the emulation of the quantum computer is running on the whole cluster. And this has two advantages. First is you can emulate more qubits depending only on the amount of memory your cluster has in total. And it also is much faster, as you see on the plot on the top right. So you can go down from days to hours in emulation time. So obviously this was only a very brief overview. If you are interested in knowing more, just visit my poster over there, and I'm happy to answer all your questions. Thank you for your attention.
Thank you. And we have Frank next. This is wrong, right? This is all my fault. This is the right one. Okay.
That looks right. Good afternoon. My name is Frank Wilfson from TNO, the Organization of Applied Scientific Research in the Netherlands. And yeah, go to the next slide. Together with a team of around 25 scientists and developers, we work together with our end users of quantum computing, the companies, on use case-based applications. And what we now did is that we translated those use cases into a open source library where you can find ready to use optimization, machine learning, and quantum communication pipelines, which are all developed in Python and are ready to use in your use cases. So if you want to know more, please visit the poster or go to the website via the QR code, which may be visible again in some seconds.
I will leave it there. Thanks a lot.
Thank you very much.
Here you go. Right on the top right corner. All right, then we have Amir.
All right, hello, I'm Amir. I'm from Kilimanjaro, an analog quantum computing company based in Barcelona. And today I will present to you with Kili SDK, which is a toolkit designed for both analog, digital, and hybrid quantum workflows. The reason we're developing a new software development kit is because there are not many that are developed for the analog paradigm of quantum computation. And the way we've developed it is that it's a modular library that has three principal modules: the analog, core, and digital. The analog module allows you to represent Hamiltonians as a linear combination of Pauli terms. And then it also has schedules that allow you to build time-dependent Hamiltonians. Then in the digital one, you have as well like just circuits that you can develop, you can build through gates. We also offer some ansatz that are pre-built circuits that can directly go into your workflow. You have the core module that lets you manipulate quantum states and also has the model, which is basically a way to represent abstract mathematical models. And you can define them as you would write them on paper. And then these complex models can be either used for cost functions, or if you build Kubo models, they could be then translated into Ising Hamiltonians that could be directly plugged into your annealing workflow, for example. Well, when you see it again, you'll find that these three principal components can be then used to construct what we call functionals. Functionals are predefined workflows, quantum workflows, that could be directly executed on your quantum computer. So for instance, for the analog computer, you have the time evolution, and for a digital computer, you have sampling. Then these three principal components could also be parameterized. And if you parameterize a principal component, then you can use it to create a variational program. This basically means that like the parameterization interface is consistent across digital, analog, or hybrid in the future. And then you can directly construct variational programs, provide them an optimizer and a cost function, and that will directly run on your quantum computer. How can you use this currently? We have some simulation backends. One is CUDA-based, and the other one is Qtip-based. And we also offer an interface for anyone who would like to build their own simulation backend that is compatible with the library. And the other way is that you could send it directly to our new Quantum as a Service platform that we call Spectrum, that will be launched next month for beta testing. And this will directly execute on our quantum computers. If you'd like to learn more, please visit us over there in the poster session. Then my colleague and I will be there to help you with any doubts you have. Thank you very much.
Thank you. And apologies for the screen's issue. Jurek is next, and last but certainly not least. So.
We'll see, we'll see. All right.
Should I start, right? Here you go.
Yeah. Hi, I'm Jurek. I'm a PhD student from the University of Mainz under the supervision of Professor Schmidt-Kahler. And I want to talk to you about high-level control for the shuttling-based trapped ion quantum computer that we have in Mainz. Click. Yes. So I'll just start. So what you see here is the software stack in a few seconds. And we use this software stack kind of to enforce the high-level control that I was talking about. So essentially what we have going in is a Qiskit circuit. Well, yeah, okay. It's going to be a Qiskit circuit that's going into the into the software. Yeah, exactly. So we have a Qiskit circuit coming in, and then this is going through the high-level stack, so through the high-level part of the compiler. And then we start with the circuit compiler, so we actually see, is this, we go through validation, so can this actually be run on our hardware? We go through optimization, so we use TCAD methods for that, and we convert the circuit to our native gate set that we have in Mainz. And then the next step is the shuttling compiler. So we also have to optimize the movement of the ions that they undergo in the Paul trap, and maybe a little bit more detail here. So we trap these ions in this linear segmented Paul trap here, so we have them in the 1D string, and we want to optimize the movement, so we want to minimize the overall movement that these ions undergo in the trap. So what comes out of the shuttling compiler is a set of high-level operations, and these high-level operations are then translated into low-level operations, which can actually be understood by our hardware. And when I say hardware, I mean the trap and the lasers and the electronic devices that drive the hardware. Yes, and then the low-level stack, as I said, translates them into low-level operations, which are then executed, and then we then get the results from the hardware. And then just one more point in a software stack is the low-level GUI, which actually allows us to calibrate the trap every morning, because we have drifts in laser power, for example. We have drifts in magnetic field that we have to account for. So we use this GUI to actually interact with the physics that's happening on the hardware level. Yeah, and if you're interested, we can talk about this more on my poster. Back there. Sorry, you didn't hear that. All right, thank you.
Thank you.